Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll introduce you to Amazon Virtual Private Cloud, or VPC, one of the foundational building blocks of AWS. You'll learn what a VPC is, why it's important, and how it helps you securely connect and manage your resources in the cloud. We'll walk through key concepts like subnets, route tables, internet gateways, and more, all in simple terms. Let's get started. Over the years, Virtual Private Cloud, or VPC, has evolved from replicating traditional network topologies to embracing cloud-native architectures that are faster to deploy, easier to manage, and more resilient by design. It has become a core building block for modern infrastructure in AWS, powering everything from small applications to global-scale platforms. Every AWS deployment, whether simple or complex, starts with a VPC. It acts as the foundation for your infrastructure, a canvas upon which all other services are layered. Without a VPC, no compute or data layer can effectively operate in isolation or at scale. A VPC is a logically isolated section of the AWS cloud that allows you to define and control a virtual network environment tailored to your application and business needs. It provides the framework within which you can launch AWS resources like EC2 instances, databases, containers, and more, all in a secure and customizable virtual network. Amazon VPC brings the structure and familiarity of traditional data center networking into the flexible world of the cloud. It allows you to define IP address ranges, organize resources into subnets, configure route tables, and manage internet and VPN connectivity through gateways. For businesses, Amazon VPC unlocks several critical advantages. It ensures enhanced security through layered controls, enables resource isolation for better governance, supports flexible configurations to meet diverse workload requirements, and allows seamless hybrid connectivity with on-premises networks. VPCs are widely used for hosting scalable web applications, enabling hybrid cloud solutions, setting up disaster recovery systems, and designing multi-tier network architectures where services are separated by function and security requirements. Amazon VPC itself is free to use. There are no charges for creating or using a VPC. You only pay for the resources provisioned within it, such as compute instances, NAT gateways, or data transfer between availability zones or on-premises networks. At the heart of every Amazon VPC lies a set of core components that work together to create a secure, flexible, and highly available virtual network. Understanding these components is essential to building a solid foundation for any workload in AWS. It all begins with the CIDR block, a range of IP addresses defined using classless interdomain routing notation. This is where you establish the size and structure of your network. For example, a CIDR block like 10.0.0.0/16 provides up to 65,536 IP addresses, offering ample room for growth as you deploy applications and services. This address range forms the backbone of your VPC and sets the stage for all networking operations. Within this IP range, you create subnets, smaller segments of the network that allow you to organize and isolate resources. Subnets can span different availability zones within a region, helping you build fault-tolerant architectures with high availability. You can designate subnets as public or private depending on whether they need access to or from the internet. To manage how traffic flows within your VPC and beyond, route tables come into play. Each subnet is associated with a route table that defines where network traffic should go, whether it's moving between subnets, reaching other AWS services, or connecting to the internet. When internet access is required, an internet gateway provides the path. It attaches to your VPC and enables resources in public subnets to send and receive traffic from the internet. This is a key component for applications that need to be accessible to external users or services. For controlling traffic at the network boundary, network ACLs offer a stateless firewall mechanism at the subnet level. They evaluate traffic rules for every packet coming in or going out and are useful for enforcing additional layers of security across subnet boundaries. Finally, VPC endpoints enable private connectivity to AWS services without sending traffic over the public internet. These endpoints enhance both security and performance, especially in regulated or sensitive environments, by keeping data within the AWS network backbone. This illustration presents a well-architected Amazon VPC, designed with best practices in mind for security, scalability, and high availability. At the core, we see a VPC defined with a CIDR block of 10.0.0.0/16, providing a broad IP address range to accommodate a wide variety of resources. Within this space, the network is carefully segmented into smaller subnets, each with its own unique CIDR range. These subnets are distributed across multiple availability zones, ensuring that workloads can remain operational even if one zone becomes unavailable. Inside each subnet, we find EC2 instances and other application components. The illustration highlights security enforcement through features like security groups and network ACLs, which work together to control traffic at both the instance and subnet levels. These measures help isolate workloads and limit exposure to unauthorized access. Around the perimeter of the VPC, we see key networking components. An internet gateway enables connectivity for public-facing resources. NAT gateways allow private subnets to access the internet for updates or API calls without making them publicly reachable. In some cases, secure links such as VPN or AWS Direct Connect may be used to integrate the VPC with on-premises data centers. This layout enables a mix of public and private workloads, offers zone-level redundancy, and enforces strong security boundaries, giving you a robust foundation to deploy resilient, cloud-native applications. IP addressing is foundational to building any network in AWS. It determines how resources communicate with each other and with the outside world, and how securely and efficiently those connections operate. In AWS, IPv4 addressing is the primary scheme. Each VPC is assigned one or more CIDR blocks, which define the range of IP addresses that can be used. These blocks can be sized from /28, offering 16 IPs, up to /16, which provides 65,536 IP addresses. For growing environments, AWS allows you to add secondary CIDR blocks, giving you flexibility to expand your address space without creating new VPCs. Alongside IPv4, AWS also offers IPv6 support. You can enable dual stack mode, assigning an Amazon-provided /56 IPv6 CIDR block to your VPC. IPv6 addresses are globally routable and help prepare applications for modern internet communication, especially as IPv4 availability continues to shrink. For public connectivity, elastic IP addresses are used when a resource needs a static IPv4 address that persists across reboots or replacements. These are public IPs managed by AWS that can be reassigned as needed, offering both stability and flexibility. Understanding IP address persistence is also important. While private IPs typically remain attached to an instance, public IPs assigned automatically may change if the instance is stopped. Elastic IPs help avoid this issue when a fixed address is required. For organizations with their own IP ranges, Bring Your Own IP allows importing public IPv4 or IPv6 addresses into AWS. This is useful for brand consistency, whitelisting scenarios, or migrating existing infrastructure into the cloud. Finally, IP addresses play a critical role in network security. IP-based rules are foundational to segmentation and access control, used in firewalls, routing policies, and monitoring systems to enforce safe communication patterns. Mastering IP addressing in AWS equips you to design scalable, secure, and manageable cloud networks. Establishing internet connectivity in AWS begins with two key components: the Internet Gateway and the NAT Gateway. Each plays a distinct role in enabling secure access between your VPC and the outside world. The Internet Gateway is a horizontally scaled, redundant AWS-managed component that provides bidirectional connectivity between resources in your VPC and the public internet. It's essential for enabling communication from public subnets, such as those hosting web servers or public APIs. Designed for high availability, the IGW imposes no bandwidth limits, scaling automatically as your traffic increases. For resources in private subnets where inbound internet traffic must be blocked, a different approach is required. NAT, or Network Address Translation, allows resources in private subnets to initiate outbound internet connections while preventing inbound access, an ideal solution for downloading updates or calling external APIs without exposing services publicly. The NAT Gateway is a fully managed service, offering a significant advantage over traditional NAT instances. There's no need to manage EC2-based infrastructure, monitor capacity, or patch the OS. It automatically scales to support throughput up to 45 GB/s, handling traffic spikes seamlessly. To achieve high availability, it's recommended to deploy a NAT gateway in each availability zone where private subnets exist. This eliminates single points of failure and ensures traffic routing remains local to the zone. NAT gateways incur hourly charges and data processing fees based on usage. Efficient design can help manage these costs, particularly in large-scale or data-intensive environments. From a security perspective, NAT gateways support egress-only communication, minimizing exposure. Combined with tools like VPC flow logs, you gain visibility into traffic patterns for auditing and compliance. Together, Internet and NAT gateways provide the essential bridge between your AWS environment and the Internet, balancing performance, availability, cost, and security. Securing your AWS environment begins with two core components of VPC security: security groups and network access control lists, or NACLs. These tools work at different layers of your network and offer complementary protection. Security groups are stateful virtual firewalls that operate at the instance level. If an inbound rule allows traffic, the corresponding outbound response is automatically permitted. You don't need to define both directions. Security groups follow an implicit deny model, meaning only explicitly allowed traffic is permitted. They're ideal for fine-grained access control, such as controlling which ports or IPs can reach an EC2 instance. NACLs, on the other hand, are stateless filters that apply at the subnet level. Every inbound and outbound rule must be defined explicitly. Rules are evaluated in numerical order, and once a match is found, processing stops. This makes NACLs useful for broad subnet-level controls, like blocking specific traffic types across entire segments of your network. While they serve different purposes, security groups and NACLs are complementary. Use security groups for precise control over individual resources, and ACLs for network-wide filtering or deny rules not available in security groups. Understanding rule evaluation is key. Security groups only allow rules and use OR logic. If any rule matches, traffic is allowed. NACLs allow both allow and deny rules, with evaluation based on rule number order. Each VPC includes default configurations, one security group, and one NACL. While usable out of the box, customizing them is important for aligning with security best practices. When troubleshooting connectivity issues, inspect both security group and NAL rules. Check ports, protocols, source and destination, and ensure no conflicting rules exist. To enforce consistency, leverage automation tools like AWS Config, CloudFormation, or Service Catalog to manage rule sets across environments. VPC flow logs provide deep visibility into the network activity within your AWS environment. They allow you to capture detailed information about IP traffic flowing to and from network interfaces in your VPC, whether at the VPC level, subnet level, or individual Elastic Network Interface (ENI). Flow logs can be configured to publish data to Amazon CloudWatch logs or Amazon S3, depending on how you want to store and analyze the data. You can choose to log all traffic, only accepted traffic, or only rejected traffic, giving you the flexibility to fine-tune based on your needs. Each flow log record includes valuable details such as source and destination IP addresses, ports, protocol, number of packets and bytes transferred, action taken, accept or reject, and log status. This data helps you understand exactly what's happening across your network at any given time. Flow logs are generated in a structured format with fields separated by spaces. You can use the default format or define a custom log format to capture additional metadata, like VPC ID, subnet ID, or instance ID for more granular analysis. These logs can be analyzed in near real time using CloudWatch Logs Insights, enabling powerful queries to spot anomalies or filter traffic by IP or port. If logs are stored in S3, you can use Amazon Athena for SQL-based querying or integrate with third-party SIEM tools like Splunk or Datadog for security operations and dashboards. Flow logs are particularly useful in security use cases for detecting unauthorized access attempts, identifying unusual traffic patterns, or verifying that your firewall rules and route tables are behaving as expected. For troubleshooting, flow logs help identify dropped packets, misconfigured security groups, or issues with routing and NAT behavior, all without logging into the instance itself. While flow logs offer powerful insight, They can generate a large volume of data. It's important to manage costs and performance by defining scope wisely and using log filtering or aggregation techniques to capture only what's needed. VPC peering provides a secure and private way to connect two Amazon virtual private clouds, allowing resources in each VPC to communicate as if they were part of the same network. This connection is established directly using AWS's private infrastructure without traversing the public internet or requiring a VPN. VPC peering is non-transitive, meaning if VPC A is paired with VPC B and B is paired with VPC C, A and C cannot communicate through B. Each pair of VPCs that needs to talk must have a direct peering connection. Additionally, overlapping CIDR blocks between VPCs are not allowed, which helps avoid conflicts in IP routing. Peering is not limited to VPCs within the same region or account. With cross-region and cross-account peering, you can connect VPCs that span different geographies or are owned by different AWS accounts, extending your architecture while maintaining isolation and security. Once a peering connection is established, you must update the route tables in each VPC to allow traffic to flow. This step is critical, as the peering connection itself does not automatically modify routing behavior. Routes need to be explicitly defined to reach the IP ranges of the peer VPC. For better usability, DNS resolution between VPCs can be enabled. This allows instances in one VPC to resolve private DNS names of resources in the other, making it easier to discover and connect to services without relying on IP addresses. However, as your environment grows, managing many peering connections can become complex. Each connection is point-to-point, and this doesn't scale well in environments with dozens or hundreds of VPCs. In such cases, solutions like AWS Transit Gateway offer a more scalable alternative for hub-and-spoke network architectures. To ensure that peering connections remain healthy, you can monitor them using CloudWatch metrics, VPC flow logs, and route table checks. These tools help validate that routes are correctly configured, security controls are in place, and traffic is flowing as expected. VPC endpoints allow your AWS resources to privately connect to supported AWS services without using the public internet, NAT gateways, or VPNs. There are two main types of VPC endpoints: gateway endpoints and interface endpoints. Gateway endpoints are used specifically for Amazon S3 and DynamoDB. They integrate directly with your route tables, allowing traffic from your subnets to reach these services without leaving the AWS network. This setup is highly scalable, has no additional cost, and adds no bandwidth bottlenecks. Interface endpoints powered by AWS Private Link are more versatile. They use elastic network interfaces, ENIs, with private IP addresses inside your VPC. These provide secure and private access to a wide range of AWS services, including services from other AWS accounts or third-party SaaS providers. Interface endpoints are ideal when you need private connectivity to services beyond S3 and DynamoDB. The security benefits of VPC endpoints are substantial. By keeping your traffic within the AWS network, you eliminate exposure to the public internet, reducing the risk of data exfiltration or interception. To control access through these endpoints, you can apply endpoint policies, which let you specify who can use the endpoint and what actions they can perform. This helps enforce fine-grained control over data access. For a seamless experience, private DNS can be enabled for interface endpoints. This allows your applications to use the standard public AWS service names, which resolve to the private IP addresses of the endpoint. No code changes needed. Performance-wise, VPC endpoints typically offer lower latency and higher reliability than public internet paths, though interface endpoints can introduce slight overhead depending on traffic volume and architecture. From a cost perspective, gateway endpoints are free, while interface endpoints incur hourly charges plus data processing fees. However, these costs are often offset by savings in NAT gateway usage and improved security posture. AWS Private Link is a powerful networking technology that allows you to establish private connectivity between VPCs across different AWS accounts or regions without exposing traffic to the public internet. It enables you to securely access services over private IP addresses entirely within the AWS network. At its core, Private Link uses a service provider and service consumer model. If you're building a service, such as a microservice or an internal API, you can configure your application behind a network load balancer, NLB, and then expose it as a private link-powered service. This makes you a service provider. Other AWS accounts can then connect to your service using interface endpoints, becoming service consumers. This setup eliminates the need for VPC peering, transit gateways, or complex routing. Traffic stays entirely within AWS, reducing exposure to the internet and simplifying your network topology. It's especially useful for multi-account strategies, where you need to expose services to various teams, applications, or business units securely, even across organizational boundaries. From a security perspective, Private Link provides significant advantages. Because connections are established via ENIs with private IP addresses, there's no need to open security group rules for internet access. Access is explicitly controlled via allow listing of consumer accounts and VPCs, providing tight access boundaries. For a high availability architecture, interface endpoints can be deployed across multiple availability zones, ensuring service continuity even in the face of infrastructure disruptions. To publish a private link service, providers must configure an NLB, associate it with the correct subnets, and define service permissions to control who can connect. AWS handles the rest, routing traffic privately and securely. Monitoring is available through CloudWatch metrics, which track connection status, traffic volumes, and interface health. This allows you to ensure that services remain available and performant. When building hybrid cloud architectures with AWS, connecting your on-premises network to your AWS virtual private cloud is a critical first step. AWS offers two primary solutions for this connectivity: site-to-site VPN and AWS Direct Connect, each serving different needs based on performance, reliability, and cost. Site-to-site VPN is the more accessible and flexible option. It uses the public internet to establish an encrypted IPsec tunnel between your data center and your VPC. This makes it quick to deploy, often within minutes, and a great choice for development environments, lightweight production traffic, or as a backup path for more critical connections. VPNs support up to 1.25 gigabits per tunnel and can be scaled with multiple tunnels for redundancy. However, since traffic flows over the internet, performance can vary due to network congestion, and latency may be unpredictable. AWS Direct Connect, on the other hand, provides a dedicated, private network connection from your on-premises infrastructure directly to AWS. This bypasses the public internet entirely, resulting in lower latency, higher throughput, and much more consistent network performance. Direct Connect is ideal for high-volume data transfers, real-time applications, or compliance-sensitive workloads. It's available in port speeds ranging from 1 Gbps to 100 Gbps and can be bonded for even greater capacity. Direct Connect also supports integration with AWS Transit Gateway, enabling large-scale multi-VPC environments across accounts and regions. It requires more lead time to provision, as it involves coordination with AWS and a network provider, but offers enterprise-grade reliability and SLAs. While site-to-site VPN is cost-effective and fast to set up, Direct Connect is better suited for long-term, performance-sensitive use cases. In many enterprise architectures, both are used together. Direct Connect as the primary path and VPN as a failover to ensure high availability. Choosing the right option depends on your business needs, but understanding the strengths of each can help you build a more resilient and efficient cloud network strategy. AWS Transit Gateway is a regional network transit hub that enables seamless connectivity between your VPCs, on-premises networks via VPN, and AWS Direct Connect. It acts as a centralized router, simplifying and scaling your network architecture as your cloud environment grows. Traditionally, connecting multiple VPCs involved creating and managing a complex mesh of VPC peering relationships. Transit Gateway replaces this complexity with a hub-and-spoke model where all networks connect through a central hub. This reduces operational overhead, improves manageability, and streamlines routing. For multi-account environments, Transit Gateway integrates with AWS Resource Access Manager, RAM, allowing you to share the gateway across accounts within your AWS organization. This supports centralized network governance while enabling distributed team autonomy. Transit Gateway introduces the concept of route tables and propagation to control how traffic flows between attached networks. Each attachment can use its own route domain, providing isolation and control over connectivity. You can choose whether a VPC sees traffic from another VPC or only from the on-premises environment. In terms of performance, Transit Gateway is built to scale, supporting up to 100 Gbps of aggregate bandwidth per gateway. It automatically scales up as your traffic increases, ensuring high throughput for even the most demanding applications. For global enterprises, cross-region peering allows you to connect transit gateways across AWS regions, enabling a global private network architecture without relying on the public internet. Transit Gateway also supports centralized traffic inspection, where you can direct traffic through a security VPC containing appliances such as firewalls or packet inspection tools. This model simplifies compliance and threat detection. Finally, CloudWatch metrics and VPC flow logs provide visibility into gateway performance and network behavior, helping you monitor traffic patterns, troubleshoot issues, and optimize configurations. Amazon VPC isn't just about networking infrastructure. It's the foundation that enables secure, scalable service integration across the AWS ecosystem. Many core AWS services are designed to work seamlessly within a VPC, allowing you to define how and where they run and how they connect to each other. With Amazon ECS and Amazon EKS, you can deploy containerized applications using VPC networking modes. This gives you fine-grained control over how containers are assigned IP addresses, how they reach other services, and how traffic is secured through security groups and route tables. Services like Amazon RDS and Elasticache benefit from being placed in private subnets, isolating them from direct internet access while enabling tight control over who and what can connect. This is critical for protecting sensitive data and ensuring compliance. AWS Lambda functions can also be configured to run inside your VPC. This lets your serverless code securely access databases, microservices, or legacy systems hosted within private subnets without needing public endpoints. For incoming traffic, the Application Load Balancer (ALB) integrates with VPCs to distribute requests across targets in multiple availability zones. It enhances both performance and availability while supporting advanced routing techniques such as path-based or host-based routing. Amazon API Gateway also supports private endpoints, allowing you to expose APIs only within your VPC. This is ideal for internal services or for meeting strict security requirements by eliminating public internet exposure. Interface VPC endpoints play a crucial role in enabling private connectivity to AWS services like S3, DynamoDB, or third-party SaaS offerings, using private IPs within your VPC. By integrating services through your VPC, you establish network-level controls that enforce access policies and segmentation, improving both security and operational clarity. This integration forms the backbone of any well-architected AWS environment. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.